that occur in point of interest here. You have one equation, okay, BR dot is equal to the minus the horizontal divergence of VBR, and you would like to discover the velocity field at the core surface. And the velocity field has two components, the V theta, the V phi component, right? So you'd like to find two components at every point using only one equation. So it should be apparent to everyone that that's almost certainly not enough information to discover the velocity field V. You can't find those two components of the vector field from one equation. So you actually need another constraint to essentially give you any chance of solving for V. And it turns out that there is another constraint that seems fairly reasonable that presents itself when you think about the Navier-Stokes equation. Now the question is, how much do I want to go into this? Do I want to go into this? Yes, maybe I do. Okay, so what we need to do is we need to look at the Navier-Stokes equation. So maybe you had something like this from Alex this morning. I hope so. So we've got inertia, we've got the total derivative of the flow V with respect to time. We've got the Coriolis force. Did we have the Coriolis force this morning? No, we weren't spinning. So we have the Coriolis force for a rotating system, balanced by a pressure gradient, balanced by buoyancy forces, balanced by viscosity, and balanced by the Lorentz force, J cross B, which looked different this morning, I think. Okay. Now, what is big here and what is small? Okay. So in the Earth's core, the viscosity is negligible in the Earth's core. Maybe in boundary layers you might want to worry about it, but its viscosity is very small. And if you work out, if you take my flow velocity of 0.5 millimeter per second and you work out the advective term, so if you look at the size of u dot grad u compared to the size of the Coriolis term, you know the rotation speed of the Earth, we know omega, we know the density, we know the velocity. So if you compare this term with the advective term, which is rho u dot grad u, you'll discover that this term is much smaller than the Coriolis force, and that essentially defines the Rossby number, and the Rossby number here is, so the ratio of the two is something like 10 to the minus 6, 10 to the minus 7. So I'm going to claim that this term is small. I'm going to claim that this term is small. I'm going to claim that this term is dominant, the Coriolis force. It's balanced by the pressure gradient. It's certainly driven by buoyancy, but buoyancy is always radial. And then the next question is, how strong is the Lorentz force at the core surface? And for that, we're going to need an estimate of not only the magnetic field strength, but also how fast it's varying. And if you take that term J cross B, remember, J is 1 over mu naught curl of B, so you need this term, 1 over mu naught rho curl of B cross B, and you work out what it looks like at the core surface. You'll see that there are some terms like BR dB by dr that you really ought to know. So a lot of it hinges on how quickly the field changes with depth. But it seems like a reasonable approximation. For example, if you look at the size of this term, BH dot grad B, if you just put in the observed values of B at the core surface and you compare them to the size of the Coriolis force. So the size of the Coriolis force is 2 omega u, and this is the Lorentz force L. then the Lorentz force at the core surface is about 10 to minus 3 compared to the Coriolis force. If you go deeper into the core, the Lorentz force almost certainly becomes stronger, the magnetic field becomes stronger, and that ratio will become bigger. But at the core surface, it's small. So this is the argument that says we can probably neglect the Lorentz force at the core surface, and therefore the motions are deemed to be well, close to geostrophic. They're certainly tangentially geostrophic. So the horizontal components are geostrophic, which means that essentially it's a little bit like the leading order for the Earth's atmosphere, that you have essentially Coriolis forces balanced by pressure gradients at the core surface. It's a hypothesis, but let's go with it. Let's see where it leads. And you might find the results persuasive. You know, maybe you think, oh well, there's something in this idea. So this is this theory which we call tangential geostrophy. So I've neglected everything at the top of the core other than the Coriolis force, the pressure gradient, and buoyancy. And if you then take the curl and look at the horizontal component, I won't do it, you will find that you get this equation, the horizontal divergence of u. Remember, at the top of the core, u is entirely horizontal. The horizontal divergence of u cos theta is 0. Well, we are, so the viscous boundary layer at the top of the core is of the order of 10 centimeters thickness. That's the idea. If you take the so you take the viscosity of the core, which is close to the viscosity of water. Well, we assume it's the same as the viscosity of water. We don't know it terribly well, and you're in a very rapidly rotating system, so you have an Ekman boundary layer which is of the order of 10 centimeters in thickness. So everything that we're thinking about here in terms of flows is really representing what is happening just below this viscous boundary layer.
How you model the rotation?
Say, pardon?
Fixed rotation with constant angular momentum or rotation of the core?
Rotation of the core and angular momentum.
It's angular speed.
Yeah.
Is constant with that outer thing, or that is different, or differential rotation?
You might be getting ahead of the game here. I'm not quite sure what your question is, but in isolation, the
How do you model the rotation?
So there is a
How do you model the rotation? Constant omega, that's what you do. Coriolis force is asking.
Yes. Omega is the rotation speed of the container, which is the mantle, right? The boundaries. It's the speed that the mantle is spinning, and the
same speed as Earth is spinning, or different speed?
Yeah, same speed that the Earth is spinning with. Yeah. Okay. Yeah. Just the speed of the mantle. Yeah. So omega is known precisely. We're going to see in a moment that there are some very tiny variations in the rotation speed of the Earth. But for the moment, we'll pretend it's constant. Okay, so that was a crash course in exactly how we come to get this other constraint, which arises when we neglect Lorentz forces. And the good thing about it is that we've now got two equations governing the two unknowns, the velocity field, the v theta, v phi components of velocity field. So we're in with a chance now. Okay, that's the good news. We're in with a chance. And indeed, it seems to be fairly reasonable. Okay, so let's now just see how we calculate these flows. So we use a representation for the velocity in terms of two components. They're called the poloidal and the toroidal components of the flow. And this is the key thing, I suppose, is that this is a complete representation of any tangent vector field on a spherical surface. So it's completely general. It's sufficiently general for our purposes. And then so it's governed by, there are two unknown scalars, this T and S. And then, of course, we just expand everything in spherical harmonics, very convenient, with a set of coefficients S and T. And we're going to stick those into the induction equation. And let's just go back to the induction equation. The key thing about it is that it's linear. If I give you these numbers on the left-hand side, and I also give you these numbers here, and I ask you to find the flow V, you can see that V is linear in these numbers, which are essentially the data. This equation is also a linear constraint on V. So if we just substitute this representation into the induction equation, you can imagine that we get an equation something like this. B dot is, so this is now a vector. B dot is AM, where A is a matrix and M is, have I put this? No. So M is the, yes, I put it here. M is the vector of model coefficients T and S. So that's what we want to find, the model M. So we just have a big, nice linear set of equations. Data here, a known matrix, and the model coefficients. And then the other thing, the tangentially geostrophic constraint, is another linear equation. Gm is 0. And we just solve these as a linear inverse problem. Now, I'm not really going to go into the details of how that's done, but it's a linear inverse problem, and you need to add some information in terms of smoothness constraints, things like that. But let's look at some results, okay? So here's an example of a tangentially geostrophic flow for 1970. And so this is the Pacific hemisphere here. This is the Atlantic hemisphere here. And you can see that we've got this strong flow heading across Africa and then sort of returning down along the South American coast. And we also have this flow like this in the Northern Hemisphere. So although it's perhaps not as clear in the Northern Hemisphere, you've kind of got two big gyres taking the field with them. So you can see that this is exactly what's needed, because we saw in the movie, we saw those spots moving across the Atlantic. So we clearly need a fluid motion to advect those spots across the Atlantic. So that seems to be doing exactly what we might expect. Okay. And here you see 20 kilometers per year. This is the size of the flow vector. You'll see that's fairly representative of the kind of flow speed here in this hemisphere. Now, we should say that things seem very different in the Pacific hemisphere. The flow speeds are a lot slower, and indeed when you look at the core field maps, that's because the features seem to not move very, very much, or not very coherently. So you seem to have two different hemispheres. This is sort of the flow of the liquid metal. I mean, if you believe everything that I've done so far, and I hope you do. Sometimes I do. Sometimes I think, do I believe this at all? No, this is the flow of the liquid metal at the top of the core that is responsible for the secular variation that we see at the Earth's surface. So it's the flow just below the the viscous boundary layer that is moving the field with it. Remember, we've made quite a few assumptions actually, but we've taken Alex's Lundquist theory, and so we've got zero diffusivity. Everything is frozen in. The field lines are frozen in. They just move along with the flow. We've made lots of assumptions, but you know, I'm pretty nicely on time. By the end of the lecture, I'll give you certainly 2 pieces of evidence that that I hope will convince you that we are not too far off track. There must be some, you know, truth in this.
20 kilometers per year is quite a large value.
20 kilometers, yeah. It's sort of the fastest thing that's taking place in the interior of the Earth, yes. But then remember, the liquid metal is very fluid, you know, it's like water, we think. So, but compared to the speed of plate tectonics, for example, which is 10 centimeters per year, then this is pretty fast. But it's, you know, it's also pretty slow compared to the atmosphere and oceans. Okay, well that just does the same thing. This shows you the what's been happening over the last 150 years. I just put some traces into the flow and allowed it to advect the traces forward in time. But one of the key things is you will see that there are some regions on the Earth where you can see this time variation in the flow. In this region here, the flow tends to be so strong that any time variation kind of gets wiped out by the strength of the underlying background flow. But in regions where the flow is not so strong, you can see these sort of funny little loopy patterns. Now, I'm going to tell you in some detail, it won't take too long, but I'm going to tell you about the work of the group in Grenoble, who in the last 5-6 years have been responsible for some work that you know, as I say, I hope will convince you that that there's some truth in what I've been trying to tell you. And the evidence comes from a completely different field. In fact, it comes from the rotation of the Earth. So if you sit on the Earth's surface and you look out into the heavens, looking at distant stars and you know, timing how quickly they come around, you find that in fact they don't come back around at the point you think they should do. If the Earth's rotation was completely uniform, sometimes they come around a little too early, sometimes they come around too late. It tells you that the rotation rate of the Earth is not quite steady. There are small fluctuations in the rotation rate. And we call that the length of the day. The length of the day is the time that it takes for one rotation, of course. So the length of the day is measured in seconds. And there are small fluctuations. So let me remember. The length of a day is 86,400 seconds. And you can see small fluctuations in the length of a day of a few milliseconds. And this is all very well documented. This is obviously very, very accurately measured in recent times. But if you go back into the past, you can also measure it very accurately. And again, it's just from these telescopic observations of objects in the sky and seeing where they are. So this is the last 150 years of the length of day. And you'll see that there is a small gradual slope in the length of day. So I've put that in as a dotted line. And that gradual lengthening of the day, anyone know why the day is getting longer? So the rotation rate of the Earth is gradually slowing down. Why is that?
Possibly due to not tidal effects of the moon?
Tidal effect of the moon. Okay, that's very good. So the moon affects the rotation rate of the Earth and gradually slows it down. So that effect is about 2.4 milliseconds per century, and that's this line here. But on top of that line, you'll see that there are considerable variations of the order of a few milliseconds, plus or minus a few milliseconds, taking place on time periods of decades. And now if we zoom in on a little period like this in the green box and we blow it up, we see the length of day is the yellow line, and in fact you can see a very strong annual signal, and that annual signal is because of the exchange of angular momentum between the solid Earth and the atmosphere, and to some extent the oceans, but largely the atmosphere. In fact, there's some fantastic work from the 80s where they started to measure the actual zonal winds in the atmosphere, so you can actually work out how much angular momentum there is in the atmosphere, and when you compare that to the angular momentum that you are losing from the solid Earth, you find that the agreement is quite spectacular. I haven't got a slide, but it's one of my favorite slides. It's really a fantastically accurate theory showing that on short periods, around about the annual period, did I say diurnal earlier? I'm sorry if I did. I meant annual. Around about at the annual period, the correlation between the atmosphere and the solid Earth is amazingly good. Okay. So this is the line of argument that we're going to look at, because this variation in the length of day that occurs that you can see very accurately on decadal and a few decadal timescales must indicate that there is an exchange of angular momentum between the solid Earth and some other object, and that other object is thought to be the core, and in fact I'll show you the evidence that it is the core. So the core and the solid Earth seem to be exchanging angular momentum, and the question is, can we actually see that exchange of angular momentum? So that's a very busy slide that's probably saying exactly what I've just seen. I've just said all that, so that's for you to read at your leisure. Now we can actually image core flows here at the surface of the core, and this all goes back to the. I didn't really prove the Proudman-Taylor theorem, did I? But so if if we adopt this, so I'm going to neglect Lorentz forces to begin with. If we adopt this as sort of zeroth order force balance in the core, and I neglect buoyancy to begin with, okay, and I take the curl of this equation. So I want to get rid of the pressure. I'm not interested in the pressure. So let's take the... Can you see that green? Green's not a great color, is it? So let's just take the curl of 2 omega cross u is equal to minus grad p. If we take the curl of this, and I'll leave this for you as an exercise for you, you will find that you get du by dz. This is you just use the vector algebra rules, curl of A cross B. Yeah, just use the rules. You'll find that du by dz is equal to 0. Okay, and this is the so-called Proudman-Taylor theorem. Which applies to very rapidly rotating bodies, and I'm sure that we're going to see more of this later this week. Emmanuel, at the very least, and Chris tomorrow will show you. They'll show you some numerical evidence at the very least. But it's a tendency for fluid motions to have a rigidity along the rotation axis. So imagine you have a little vortex of fluid here. You'll find that it's doing exactly the same thing at all points along the fluid. Now, if you want to work out the angular momentum of the fluid, and you have observations at the core surface here, you can plausibly imagine that the same core motions are occurring everywhere. Everywhere in depth in the core. And if you want to calculate the angular momentum carried by flows, the only part of the angular momentum you want is the axisymmetric part. So in a way, the angular momentum depends on these kinds of cylinders that I've drawn on this diagram, which we call geostrophic cylinders. Okay, so now, if you look at the way that the large-scale zonal coefficients vary in time, so these are the coefficients that are capable of carrying angular momentum, what you find is that I've plotted the first 4 zonal coefficients. So these are the ones that are responsible for flows which are going around the rotation axis, and they either have even or odd symmetry with respect to the equatorial plane, so they have a certain parity. And the ones plotted in red are these with a symmetric parity. These are the coefficients T10, T30. You see how they're evolving in time. So this is the last 150 years, and this is the result of a calculation, a frozen flux calculation of the flow in the core. So you've got quite a lot of variability in the symmetric component of flow. And then in blue, we've got the antisymmetric component of flow, which seems to be relatively steady in time. Or it doesn't show such large oscillations as the symmetric component of the flow. And these large oscillations of the symmetric component of the flow are compatible with the idea that they represent the motion of cylinders around the axis, which are carrying angular momentum. They're carrying angular momentum because of a coupling between the core and the mantle. So that was my own work from a few years ago, but I'm going to show you the work of the group from Grenoble. So again, this is in words, just to tell you how you can work out the angular momentum of the core, and you can work out what the change in the length of day should be based on the angular momentum of the core, and so on. So if I show these early results to start with, and then I'll show or maybe I just go straight to the Grenoble results. Let's just go straight to the Grenoble results. So the Grenoble group have carried out this exercise. They've carried it out using a special kind of approximation that I think it's not appropriate to go into. They've retrieved the core flow, and this is their result from their paper, which is just on the website just now. So these are the these isolines again are these are contour. Let's see what they're. Well, they're sort of they're streamlines. They're streamlines, and yeah, they're streamlines of flow. Okay, so the flow just follows these streamlines. Yeah. So remember me, I was pointing out the two gyres. I pointed them out in the earlier model. So these are the two gyres that you see. This is the Atlantic hemisphere here. So the gyre is strong in the Atlantic hemisphere, and there's not much going on in the Pacific hemisphere. So that's their results, which are not very different from many other people's results. But when you let's see, let me get this. Okay, when you look at how much their results, how the time variability of their results predicts the length of day change, then the length of day, I think, that we measure geodetically is in black, and the predicted changes that Gillet and workers make are in red. Okay, so that's over the last 70 years. And maybe I'll go back to my own diagram. You can do this for the last 150 years or so. So the black dots here are the black dots are the actual observed length of day change, something like plus or minus 3 milliseconds, and the different lines are different predictions from different flow models. Using different amounts of smoothing. So it gives you some idea of the kind of room for maneuver you have, but you certainly see that you can certainly predict all of this swing in the 20th century in the length of day. Now, that's probably not the most impressive thing. The most impressive thing comes from looking at a slightly different wave band in the length of day, and it is it comes from looking at the spectrum of the length of day. So let's take the length of day series and do a Fourier analysis and look at the power in the different period ranges. And this was a very important paper, came out in 2000, and what you have here is the observed power in the length of day signal, the solid black line. So this is the spectrum of the length of day with this bump in the kind of 8 to 6 year period range. And now the first question that was asked was, could it be that the atmosphere or oceans could explain this bump in the length of day signal? I mean, if the atmosphere and oceans were taking up angular momentum on that period range, then we would be able to actually see it. We can actually work out what the angular momentum in the atmosphere and oceans is. And this line here is the angular momentum in the atmosphere and oceans, and they don't show any peak. It doesn't show any peak in this wave band, and indeed this peak in the length of day spectrum is thought again to be the result of the angular momentum exchange with the core. So having seen this bump, this is exactly what the Grenoble group went after. They went after trying to explain this bump in terms of angular momentum exchange with the core. And they wanted to ask, can we see the fluid motions in the core that are associated with such an angular momentum exchange? Now, that's really a difficult thing to do. That I can tell you that the signals you're trying to retrieve are very small. But I'll show you what they've reported, and this is all very new stuff. Well, no, I'll show you what they reported first, and then I'll explain it. So, in a paper in 2010, they filtered the time-varying zonal flows that are responsible for the flows around the rotation axis. They filtered them in the wave band of something like 5 to 9 years. So they just looked at the variability of the zonal flows in that wave band, and they plotted, as a function of time, the phi component of the flow, so it's this component of the flow, as a function of cylindrical radius. So this is the rotation axis, and S is the cylindrical radius, the distance from the rotation axis. And this is what they saw in the time variability of the phi component of the flow. So you see that you have flows of alternating sign. The u phi is going one way, then it's going the other way. And you'll see that it kind of propagates out from this position here towards the equator. So S equals 1 is the equator here. And this solid black line here is actually this S position here, which is just equivalent to the tangent cylinder that fits over the inner core. So that's what they saw in the u phi. Remember, u phi has been derived here from the magnetic data alone, and from the frozen flux analysis of the magnetic data. Now, if you take these flows and you can then calculate what the angular momentum of the core would be, and that's what they did, and that's on this figure here. So the angular momentum of the core is the, I'm certain that it's the black line. I'm not certain, actually. Doesn't actually matter. One of them is the angular momentum of the core, and the red line is the angular momentum of the solid Earth. So the fluctuating angular momentum of the solid Earth. You always have to exchange the sign of one of them. The idea is that the angular momentum is conserved between the solid Earth and the core. So if it's conserved, that means if one of them gains angular momentum, the other one must lose it. So you just need to reverse the sign. But this is their prediction then, with the sign change, of the length of day changes in this wave band of about 6 to 9 years. So what they see is an incredibly good phase match and also amplitude match between the observed 6 to 9 year angular momentum changes and their predictions. So that's all very impressive. And that tells you that, I think it tells you many things. It tells you that this whole procedure that we've gone through based on frozen flux and geostrophy, etc., is a reasonable way of treating the data. And it tells you that the core and mantle are interchanging angular momentum. The mechanism for that is not determined. It doesn't really matter. This is a sort of, we would call it a kinematic study. It doesn't really matter. So you have a sort of an explanation for this bump that I showed you, coming back to this work of Abarca del Rio. You have an explanation for this bump in the length of day spectrum that you see around about 8 years.
What about this linear? Here, the left.
Well, once you go up to longer periods, we know that we certainly know that there are. Let's go back to the length of day signal. So you know that once you get out to decades, there is a lot of power in the length of day. That's not a problem. In a way, what we're looking at is the sort of the 6 to 8 year signal that is wrapped up in this in here. Maybe it's not very well plotted here. But that's the key thing. And you know that as you go to these. You also know as you go to short periods here, again, you've got this peak here is all to do with the annual signal and the exchange with the atmosphere. I'm not actually show that there is an explanation for this Fourier peak. Now, here is the final thing just to say, because this is of interest. And Alex this morning talked about how a magnetic field line has elasticity. Doesn't like to be stretched or sheared. And if you have a fluid motion, which let's take a differential rotation of the fluid here, a u phi, which goes in opposite directions. U phi stretches and shears that magnetic field line. That field line can provide an elastic force which wants to bring the fluid motion back to its equilibrium position. But in doing so, of course, it can actually, it imparts an inertia to the fluid, which then overshoots, and you can actually set up a wave motion. The actual reason for the fluid line not wanting to be stretched is that there's a Lorentz force J cross B that acts back on the fluid to try to restore the field line to its unstretched state. So I don't know if that diagram is helpful, but if you displace two adjacent cylinders, they can start to oscillate with respect to one another, and the field line that is threading through them can provide the restoring force to to actually sort of, it maintains that oscillation. So this is very old theory going back to Taylor's paper in '63, and then the theory for it was actually written down by Broginski in 1970. And what we see in the observations, first of all in the first paper of Gillet, is that we see these waves which seem to travel across the core surface, across the core. They're traveling across the core. They're rigid cylinders, and the waves are traveling outward from the middle of the core outwards. They seem to be initiated here, and this place, remember, is right here. This is the tangent cylinder. So Gillet et al. Think that these are torsional waves that are initiated at the tangent cylinder and which travel out to the core surface. Now you'll notice, so this is the equator, remember. You'll notice that there is a sort of kink here in the travel of the waves, and this was from their analysis 5 years ago, and they have redone this analysis, and it's just on the web server right now. So this is the new analysis over a longer time period. This is from 1940 to 2010, and well, there are several things. First of all, okay, the colors have changed. That's not too important. The diagram has been flipped so that this is now the equator, right? The equator on the previous one was at the top, so the waves are now traveling in this direction. Here is now the, well, maybe it's not so obvious, I'm not sure which to point at, but there is still this kind of kink in the traveling of the waves. And what they've done is to plot on some theoretical speeds that the waves would travel at for certain values of the interior magnetic field strength. See, what I didn't say was that it's the actual traveling of the waves. The speed at which they travel is indicative of the strength of the magnetic field. So they actually travel out with an Alfvén speed, where the Alfvén speed is, well, the Alfvén speed itself is proportional to the S component of the magnetic field. So if you see these waves traveling, you can actually deduce how strong the magnetic field should be in the interior of the core. And in their first paper, they felt that the appropriate speed was something like 2 to 3 milliteslas in the interior of the core, with a slightly lower value of magnetic field here. So these are traveling quickly, and they slow down here. See, it takes longer to travel this last little bit. So the waves are slowing down. That tells you then that the S component of the B field must be weakened, which tends to make sense. As you expect the B field to be weakened as you get close to the surface of the core. So that was their work from 5 years ago. This is their current work, and the numbers that they've given for these propagation speeds, then this is appropriate for 2 milliteslas, and this is appropriate for 0.6 milliteslas. Does anyone remember, this is probably an unfair question, but let's not ask it, I'll just go back to it. I was going to ask you if you can remember how strong the magnetic field is at the core surface, but I'll show you instead. Pardon? Gauss. Oh, 3. 0.3 milliteslas. Very good. Yeah. It's getting up to. So this is getting up to about 1 millitesla here in the strong regions. So we know that the field is of the order of 0.3 milliteslas, as you quite rightly say, at the core surface, and Gillet's work says, well, look, these waves are compatible with traveling the last the last 10-20% of the distance over the core through the core with a speed of about 0.6 milliteslas. That seems very much in accord with what we might expect, and I think almost certainly tomorrow we're going to hear from Chris that an increased strength of magnetic field in the interior of a dynamo capable planet is very much expected. So this sort of number, 2 milliteslas for the core of the Earth, seems about right, about a factor of 10 or so increase in the interior of the core. So that all looks like a very intriguing picture. This is a very unique thing because it is essentially one of the only probes that we have looking into the interior of the core. The only way we can look into the core is through the dynamics. And this sort of analysis provides the framework for understanding the dynamics. I think the other impressive thing that they've managed to do, who can fail to be persuaded by this kind of phase and amplitude relation that they have between their predictions and the observations. So that's all built, just to recap, that's all built on the frozen flux theory for the secular variation, right? There's no diffusion in there at all. It's built on some very simplifying assumptions about the dynamics. There was room for it to fail. It could have failed. It seems to work okay. It brings predictions that seem to then be corroborated by other lines of geophysical evidence, and it provides the window into the core. It provides us with a couple of numbers for the interior field strength. It does not tell you how the exchange of angular momentum is taking place. This is really kinematic. You just image the flows. You just see what the flows are doing. You can't really see what is mediating the exchange of angular momentum. But for my money, that's all very, very impressive work, and yes, it all worked out very nicely for the French group. So that's almost everything I want to say. In fact, I think I will now stop there. There's 2 more slides, but I think I stop. So those are the references for the early work on the frozen flux theory of the secular variation. And I stop there. Thanks a lot. Any last burning questions?
So by using your models, whatever you say, is it possible to predict the reversal time, next reversal of magnetic field?
Ooh, no. You see, it's all really working on different time scales. So once you start getting into 1,000-year time scales, you remember when we did the back of the envelope calculation of, let's just go to it, what is important in the induction equation. Right, let's go all the way back here. So, you know, when I was looking at what's important, advection or diffusion, as soon as you start getting out to, well, I said that a reversal will take, observationally, is seen to take 5 to 10,000 years. So 5 to 10,000 years is a diffusive time scale, right? It all depends on the length scale of the feature, but there's my estimate, 30,000 years. So a reversal that takes 10,000 years, you may not neglect diffusion. So in many ways, so this would never have any predictive power about reversals, I'm afraid.
So this in momentum exchange time scale, you said around 5 to 6 years.
Well, that's not a time scale for exchange, but it's okay. So you may ask, why do you see this signal? Basically, you have a normal mode of the core now. The normal mode of the core, the fundamental normal mode of the core, the period is set by the interior field strength, and so you see the torsion oscillations, which are a type of Alfvén wave, being excited as a normal mode of the core. But in a way, it doesn't really say anything about it doesn't say anything about how the angular momentum is exchanged.
Oscillation time scale coming from the torsional waves.
It's an oscillation timescale coming from the torsional waves, yeah. And certainly, I mean, Chris in his numerical work, you know, he thinks that such waves tend to be excited by Reynolds stresses at the tangent cylinder more than elsewhere. So the question is, how do you excite these things? There are probably many ways of doing it.
This other one, the reduction time scale is connected to that torsional wave or no? The reduction that 60 years is 10 times more.
Oh, this estimate, I said sort of 60 to 100 years. This estimate, remember, came from this very, I think I had a picture, didn't I? It came from this large-scale flow that is advecting all those features fairly monotonically.
So it is not connected at all with the torsional waves?
No, it's not connected. Okay, let me just point out, there are many things to point out here. This is 20 kilometers per year, and don't know if it's on one of these diagrams, but right. Yeah, I think the scale is not on here, but I think this is 0.3 kilometers per year. The ratio of these are absolutely tiny little back and forth oscillations, which are riding on the back of this really quite strong background flow. So it's a good question, because I didn't point that out. I mean, I said it's all very difficult, but these are absolutely tiny little flows, which exactly how they've managed to resolve them, I'm not quite sure, but they've done a good job. So these are about a few percent, 5% or something of the background flow. Yeah, it's magic. Yeah.
I want to ask, what are the how significant is the effect of boundary conditions, the core mantle boundary conditions on the shape of the continent? So, does the shape of the continent also affect the core mantle boundary conditions?
The shape of the continents.
And oceans. The shape of the continents have been evolving since millions of years.
That's right.
So, does that also affect the core mantle boundary condition? And,
The whole mantle boundary.
Core mantle boundary condition.
Cold mantle.
Outer core and
The core mantle. So excuse me. Sorry. So the timescales again are very different, right? The timescale for changing the continental mass distribution is of the order of 100 million years. Yeah, I mean it takes something like 50 million years for a subducted slab to reach the core mantle boundary. You just take 10 centimeters per year and 2,000 kilometers. I hope it works out at about 100 million years. So, I mean, for what we've been talking about here, that has no relevance at all. But it might have relevance for some other phenomena. Let me just tell you about. Alex wrote up an open question this morning. I can write up an open question. If you look at the reversal frequency with time, so this is the present day, and this is time going back into the past, and you look at the reversal frequency. So you have about I'm not quite sure of the present number. It's something like 2 to 4. It's maybe about 4 actually reversals per million years. So this is the reversal frequency in reversals per million years, and going back in time, it drops all the way back to this is now about 90 million years ago. This is the Cretaceous. You have a long zone, the Cretaceous quiet zone, when you have no reversals at all, and then you go back to about 180 million years, which is when our records really run out, because we can't see any more seafloor. It's all been subducted. But the reversal frequency apparently reverses as you go back in time. So, I mean, this is statistics, but it's still, there's something interesting here. The reversal frequency is far from constant, and in fact, you got to a period when there were no reversals, and then prior to that, there were lots more reversals. What can be setting time? What can be setting time scales which are of the order of 50 or 100 million years? What can be setting those time scales? Again, that calculation, you take the 10 centimeters per year of subduction rate, and you take the 2,000 kilometers of mantle, 2,900, 3,000 kilometers. So it takes about 100 million years to subduct, to go from the top to the bottom. You could change the boundary conditions on a 50 million year timescale by subducting different things, changing the thermal boundary conditions at the core mantle boundary. And some people think that that's probably the thing that's responsible for altering this kind of reversal frequency. I mean, it's hard to see where you get this kind of timescale from otherwise. So anyway, it's an intriguing correlation. So that's I think the thing that maybe is relevant when you think about the continents and their influence. Yes, please.
What is the Ekman number?
What is it?
For the simulation. For the simulation, what was the Ekman number?
Actually, this doesn't involve any viscosity. This isn't. So we haven't seen any simulation that requires any Ekman number so far. There's no numerical simulation so far. This all comes from observations, yeah. This literally all comes from observations and this little bit of mixture of theory and, yeah, it all comes from observations. A lot of it is completely diffusionless, so there's no magnetic diffusion. The viscous diffusion doesn't enter into it at all. So.
Looking at this figure from 1945 to 50, I get the impression that the torsional wave is propagating backwards from the equator towards the tangent cylinder. Is it so? Because the slope of those contours are in positive, whereas in regions like year 2000 is negative.
You think of this? That would correspond to going backwards, and the year 2000. Oh, like that? Well, I don't know. I think the preponderance. I mean, yeah, you can pick out things like that, I suppose. I think the preponderance of slopes tends to be, in that direction. But I really don't know the answer. I think it would be you should be careful to believe every detail, maybe, of this. It's.
Do they suppose that torsional oscillations can move only from the tangent cylinder towards the equator, or it can be moved?
No, they don't assume it at all. No.
Does it mean that it is going back towards the tangent cylinder?
Does it mean it's going?
That the wave is going from the equator towards the tangent cylinder?
Well, that would do, but this is the tangent cylinder. That's the equator. So anything like this is going that way, but anything like that would be going the other way.
So there's not much evidence of reflection. If something comes out of the tangent cylinder towards the equator, you might expect it to sort of hit the chromatic boundary
Yeah.
and then get reflected and travel back. But there's not much evidence of that. It looks more like stuff comes out from the tangent cylinder and gets absorbed. Presumably by the
Was there another question? No. I mean, yeah, this is all very new, and I'm reporting the work of others. I find it quite fascinating what they've managed to do. Okay.
Yeah, tomorrow 9 o'clock we'll meet again.
Okay, the posters, I think you managed to meet Mansi, other people. So if you're not met, then leave the name, your name and so whoever wants to fill in the poster who has not given name to Mansi.